So we're going to talk about resonance and just delocalized electron systems in general. So what is local? What is delocal? Here we see two electrons, right? These electrons are on nitrogen. They're nitrogen's electrons. What do I mean by nitrogen's electrons? These electrons aren't shared, right? See, here, however, these electrons are shared. These aren't just oxygen of this carbon's, or sorry, they aren't just this oxygen's electrons, they're also this oxygen's electrons. Back and forth. They're delocalized, right? They're not local on a specific point. They're moving around. Okay. And the more moving around we get, the moving around of electrons like in this manner is called resonance, okay? And the more resonance we have, the more stable the compound is. So let's look at the structure of benzene. Benzene has degrees of unsaturation of 4. There's 3 double bonds, and we have a ring. These are different representations of benzene. It's flat. All the carbons are sp2. Electron delocalization gives benzene a lot of stability. Cool. This is a very, very stable structure. So all the bonds in a benzene ring are equal. And when I draw it like this, like, oh, this, and this, there's no double bond between these bonds, right? There's no double bond here, there's no double bond here. So what's exactly happening? These double bonds have resonance all the way around the structure. So this has resonance here, here, here. And all the benzene bonds are between the length of a carbon-carbon single bond and a carbon-carbon double bond. So this is a resonance hybrid. This is a better representation of this actual structure. In reality, we have 1.5 bonds across this whole thing, but there's really no way to draw 1.5 bonds. So we draw it as a dotted dot, 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 dot line. Okay, so oftentimes you'll see benzene written in this format. Okay. Hybrid structure is an average of all the resonance contributors. Okay, so in reality, we're going back and forth between these two. The hybrid is a better representation of the actual structure in, like real life, right? So for resonance requirements, you need to have resonance with p orbitals on adjacent atoms and on the same plane. So here we have no resonance because we have this twisted conformation and we don't have the same plane. Here we have resonance contributors, resonance hybrid. Cool. Rules for drawing resonance structures. So first of all, only move pi electrons or one lone pair of electrons. Never move single bonds or atoms. If you're moving single bonds, then you're changing like the actual nature of the structure, and or if you're changing the atom positioning, you're making a different structure, right? Resonance doesn't make different structures, it just moves electrons around on already existing structures. So the net charge in the molecule should not change either, okay? Like you can introduce formal charges, but you should never be introducing like a net change in charge. Only move electrons towards an sp2 or sp atom, never towards an sp3. Cool. You can move it this way, but you can't move it this way because this is sp3, this is sp2. Don't break the octet rule, no more than 8 electrons. So, the octet rule is probably the most important rule. You can't have more than any like sorry, you can't have more than 8 electrons on any given carbon, whether they be like lone pairs, bonding electrons, etc. You know. Okay. Amide, this is not actually sp3, it's sp2 because of the resonance. Because at first you might think like one, two, three, four things, right? But in reality, we're going back and forth between these two structures. So you actually categorize this as sp2. Okay. Stability of resonance structures. So these have equal stability. More stable, less stable. So basically what's going on here is that um, the more stable a resonance contributor, the more it'll contribute to the actual overall structure, right? So it doesn't necessarily like when we draw the hybrid, it doesn't necessarily mean that this is 50%, this is 50%. It just means that both these two structures contribute to it, and this is the best way that we can draw it. So again, here, when we look at these structures, the first one, they have equal stability. Uh, Equal stability basically means that this one is contributing as much to the resonance structure as this one. More stable, less stable. Less stable because of the separated charges. This one has no formal charges. This one has two formal charges. So it's kind of clear why this one would obviously be the more stable structure. Okay. This is not stable because the more electronegative atom has the plus, and we have a negative on this position. This is most stable because there's no charges. This is stable, but not as stable. It's more stable than this because at least the negative is on the electronegative atom, but this is the most stable because it's both neutral and it has full octets and it has no formal charges. Okay, insignificant contributors don't contribute towards the hybrid and shouldn't be drawn. Okay. Push electrons towards a more electronegative atom unless the only option is to move electrons away from the electronegative atom, in which case do it. Any resonance is better than none. Okay. So resonance contributors are less stable if, the most important thing, if atoms have an incomplete octet. There's an important caveat to this, but I don't think you cover it in the scope of this quarter. I think you do it next quarter when you take 109B. So I'm just gonna, not talk about it. But basically, as a little prelude, when you have an overlapping pi bond between a 2p and a 3p orbital, um, this is actually less stable than having an incomplete octet. And when you learn about something called acyl chlorides, you'll see why that is. But again, aside, you don't need to know about that for now. Having a negative on an atom that isn't the most electronegative is also bad. Having a plus on the electronegative atom, charge separation, any resonance is better than no resonance. So just keep that in mind. Even if you have like structures that we call bad resonance structures, something is better than nothing. Okay. So this is what you would expect. More stable, more stable, more stable. Delocalization energy. So the delocalization energy is the stability gained by delocalizing electrons. So the greater the delocalization energy, the more stable the structure. More stable means less reactive. The more number of stable resonance contributors you have, the greater amount of delocalization energy you have, right? So the more resonance structures you can draw, it's likely that the stability of the compound is better. And you have to also look at the quality of those resonance structures. But as we were saying earlier, um, some resonance is better than no resonance. So generally, you can just go off of the number of resonance structures. Even though dienes have more resonance contributors, carboxylate has a greater amount of delocalization energy since it has a greater number of stable resonance contributors, right? So there's, a caveat. There's sometimes a balance between the number and the stability. The more nearly equivalent structures of resonance contributors, the greater the delocalization energy. Cool. Isolated diene, conjugate diene. Conjugate dienes are more stable because of electron delocalization, hybridization as well. This structure doesn't happen. It's something called accumulated dying when you have a double bond. It's very, very unstable. You get something called locking out of the plane when you have this. In reality, it's like this is perpendicular, I think. Again, you don't need to know that. You should know that accumulated dienes where you have a double bond right next to a double bond, as opposed to separated by one carbon, are very unstable. Okay. Delocalization affects carbocation stability. So this is actually as stable as a tertiary carbocation. So when we talk about stability and shifting towards more stable positions, it's not only about the substitution, primary, secondary, tertiary, it's also about allylic or benzylic. So this has a lot of resonance structures, right? So this is a very stable carbocation. This is a tertiary benzylic. It's even more stable than just a regular benzylic. So these are the relative stabilities of carbocations. You'll see that allylic, 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 benzylic, benzylic, benzylic. Um, it should make sense, right? These are all allylic. Tertiary will be better than secondary, will be better than primary, given that they're all allylic. Same thing, all benzylic. In the hierarchy overall, benzyl cations and allyl cations are the best. Sometimes you can equate tertiary carbocations to allyl or allele cations. You kind of treat these as the same. Um, so you're never really gonna have to differentiate between these three. Like it'll always be very obvious. If that makes sense when you're differentiating. Okay, effective delocalization of electrons on pKa/acidity of a compound. Determine the stronger acid. So this has a higher pKa, so it's a weaker acid, and that's because once we remove the acidic protons, this electron has a lone pair here, nowhere to go. This oxygen has a lone pair, nowhere to go. This can be delocalized. It can be spread out more, right? So we're taking one thing that's really bad and spreading it out, right? It's, you got a 50 on a test, you only have one test, you have five tests. Cool. Which is more acidic? Resonance structure. So the thing that's resonance stabilized will always be the thing that's more stable, more acidic, etc. Electronic effects. Replacing hydrogen with different substituents will either increase the electron density or decrease electron density. Okay, so you'll talk about these very heavily in 6Al and 109C, but basically what's happening is this group here has an effect on the overall stability of the structure. So if this group is an R group, a methyl, ethyl, anything that has a carbon, other stuff, we get hyperconjugation, so we get donation into this ring. Resonance is the other way that you can tell what's going on. Um, this is donating into the ring, and there's an easy way to test that, okay? So if I have a substituent here and I have a double bond, if I try drawing an arrow up here, I can't move these electrons anywhere else without breaking the octet rule. So if I can't do that, then that means that this is donating because these electrons have to go this way. Versus if I can do that, it's likely withdrawing electron density. And we see that here, this one here, right? I can draw this here, and this is totally okay. This is not violating any octet rule, right? Because this is positively charged. Cool. So this is inductive withdrawal and it's resonance withdrawal. Okay. Electron donating groups destabilize the base, carboxylic acid is weaker. Electron withdrawing groups stabilize the base, carboxylic acid is stronger. Okay. So when we rank these, what's going on here? This is electron withdrawal by resonance and electron withdrawal by induction. This is the most stable conjugate base, basically because we have the most spreading out of charge. This is pulling electron density. This is also pulling electron density. Here you have slightly weaker groups, weaker, 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 weaker. Okay, and I'll leave it to you to go through the specific effects of each of them. But the general idea is that you prefer to have withdrawing groups, you prefer to have stronger withdrawing groups. This one is donating groups. Um, there's also two competing effects. Sometimes resonance and induction sometimes act opposite to one another. Because you could see here that, nitrogen here with its lone pair, technically it's a inductive withdrawal, right? Because this is more electronegative than this, but the resonance effect will outshine the withdrawing effect. So you can kind of assume that if you have resonance and inductive effects, that resonance will almost always win. Um, the only time it really matters is when you don't have resonance. Cool. Which is a stronger acid. Both groups donate electrons into the ring, but the group on the left can only donate electrons because um, it can't move up this way. So we have two competing resonance structures here, right? I could move the electrons here, or I could move them here. Here I can only donate into the ring, which means that the group on the right will be the stronger acid. Cool. Effective delocalization and regioselectivity. Um, this position is preferred over this position. It just comes down to the fact that we will put our group on the most stable carbocation, right? The carbocation will form on the most stable position. Secondary benzylic is more stable than secondary. If this level of degree of substitution is the same, the one that's resonance stabilized will always win. Okay, two types of dienes. There's isolated dienes and there's conjugated dienes. These dienes have too many sp3 carbons in between them, so they can't resonate. We can't move stuff around. You might think like, oh, can I get a hydride shift from here to here? At first it might make sense, right? If you move this here to here, hydride shifts and methyl shifts generally can only occur across like one like bond, though. You can only really move from here to here. Like some people say that hydrogens aren't smart enough to move the plus here. Basically, you can only hydride shift like one position or methyl shift one position. If both intermediates have the same stability, the less stable alkene gives the major product. Cool. Cool. Conjugated dienes. We can see here these have resonance, right? So they have a resonance hybrid. This is isolated, it didn't have resonance. Okay. Thermodynamic versus kinetic control. So just simply put, the product that's formed faster is the kinetic product. The product that's more stable is the thermodynamic product. So thermodynamic means at the end of the day, this level, this final product level is lower. Kinetic means that the initial bump is lower. So you see here that this bump is lower, so it'll form faster, right? But at the end of the day, this is more stable. So this is thermodynamic, this is kinetic, this is thermodynamic. Okay, the 1-2 product will always be the kinetic product. 1,4 will always be the thermodynamic product. And I'll talk about what I mean in by 1,2, 1,4 in a second. But basically, um, 1, 2, 3, 4, 1, 2. Um, that'll make more sense when I go over it in a second. Okay. Um, okay. So you can see here that 1, 2 basically means that at the end of this double bond, we're one away. Here, 1, 2, 3, 4, it's just further away, right? It kind of maybe makes sense. As you look at more structures, you can kind of see like this is the numbering, right? So when we're dealing with kinetic versus thermodynamic, we'll always have a system of two double bonds, okay? We'll always have two double bonds that are in a conjugated system. 1, 2, 3, 4, okay? This is characteristic, at least in the context of what we're discussing right now. Um, with that, there'll always be a favored pathway. This will result in a tertiary allylic resonating with a secondary allylic. This one has no resonance, so we're going to form with this pathway. We're going to form this pathway. Okay. So thermodynamic use higher temperature. If you see a temperature value, assume that you're probably going to get the thermodynamic product, the 1,4 product. Um, this is just because it has enough energy to make it here. When we have low energy or -78, whenever you see -78, it's almost a kinetic like product. It's almost always like a kinetic product consideration. You get the lower thing, you get the blue thing because you don't have enough energy to make it over this initial bump to get here. Even though this product is technically lower in the long run, in the short term, you don't have enough to do this. Okay, cool. Okay, so benzene is aromatic. So we're going to talk about aromaticity in a second. It's just there's a lot of rules surrounding this. Right now, what you need to know is that the more delocalization you have, the more stable you are. There's a special categorization of delocalization called aromaticity, which is when you have in a cyclic system, a conjugated system, an odd number of electrons, etc. Um, anyway, let's just get right into it, okay? So, for something to be aromatic, there are a couple of requirements. There's two main ones. There's a structural and electronic requirement. For structure, it has to be planar, has to be uninterrupted cyclic array of p orbitals. So what is this saying? It just means that we have to have electron flow throughout the whole molecule, right? So we have a double bond here. This double bond can't go anywhere, right? This double bond can come down here. This double bond can go here. We get this flow, right? Like when you draw the resonance hybrid, it's a circle. So in a cyclic molecule, when you draw the resonance hybrid, it always has to be a circle. Okay. And it has to be planar. So all of this has to be on the same plane. The electronic requirement is Huckel's rule. So this is just a complicated way of saying that you need an odd number of electron pairs specifically participating in the system, right? 1, 2, 3 pairs. 1, 2, 3 pairs. Cool. A compound has to be aromatic, or if a compound is aromatic, it has to satisfy both these requirements. So let's look at a few, right? So this is cyclic, this is uninterrupted, but this has two electron pairs, so it's not aromatic. This is cyclic, this is uninterrupted array of p orbitals, but it's not planar, so it's not aromatic. It also has 1, 2, 3, 4 electron pairs. Here we have not aromatic because this is not a conjugated system. We can't move this double bond here because this is an sp3 carbon, and if I move the double bond here, I'd be breaking the octet rule. This is actually a conjugated system, but it has two pairs of electrons, so it's non-aromatic. This is aromatic because it has 1, 2, 3 pairs of electrons, and it's a fully conjugated system. Cool. Okay, aromatic heterocyclic compounds. So a heterocycle is basically a ring structure where you have a molecule in place of what you were expecting to be a carbon, right? You have nitrogen, you have oxygen, you have sulfur instead of a carbon here. So this is pyridine, okay? So at first you might think like, oh, this has 1, 2, 3, 4 electron pairs. Shouldn't that be non-aromatic? But it actually turns out it's aromatic. So what's going on here? So when I draw out this structure, this might be like overcomplicated. What's going on here is there's only three lone pairs here that are participating in this structure, okay? This lone pair is localized to the nitrogen. So in reality, it's not part of this resonance structure. It's not resonating into the ring. So you don't count it. And you're going to get this thing a lot where you have one atom and you have a bond and a lone pair on it. Just remember that you can only count it once. Like you can only count this position once in any given molecule. If you have a lone pair and a double bond on it, it'll never count as two electron pairs because there always will be this kind of characteristic thing where one set of the pairs will be involved and the other will not. Okay, pyrrole. One, two, three. sp2 orbital binds the hydrogen. This is not involved. One, two, three, planar, aromatic. Cool. If the double bond is bound to the heteroatom, do not count the one lone pair electron. If the double bond is not bound to the heteroatom, count the lone pair electron. Cool. Anti-aromatic compounds. So anti-aromatic compounds are something that have extra instability. So they're worse than just regular compounds. So the structural requirements are the same as the aromatic compounds, planar, uninterrupted cyclic array of p orbitals. So instead of 4n plus 2 pi, they have to follow 4n, which basically just means that you have to have an even number of electron pairs. So 1, 2, 1, 2, planar, uninterrupted, even number of pairs. These are anti-aromatic. So non-aromatic is basically just not following the structural requirement. And once it's satisfied this, it's either anti or aromatic. And that's based on the electron pairs. Okay, these are something called Frost diagrams. So these explain stability and instability in a molecular orbital context. So let's take a look at these. So again, we have these here, which are considered to be like, back in the first video, we drew molecular orbital and atomic orbital diagrams for hydrogen, helium, right? So this is stable, this is unstable. So we draw a cyclic compound with one of the vertices pointed down, okay? So that's the only requirement. You have a vertex, it's pointed down, okay? And then you draw it through the middle. So irrespective of how you do this, as long as you have one vertex pointed down, it'll work out to be an equivalent Frost diagram. Okay, we have 6 pi electrons, right? 1, 2, 3, 1, 2, 3, 4, 5, 6. So the way that you drew three here is one, two, three vertices, right? So you draw these lines based on the vertices, okay? So each line here corresponds with the vertex. One line here, one line here, one line here, one line here, here, here. Cool. So with that, you have two unpaired electrons in the anti-bonding molecular orbital for this one. You can see that because if they're on the line, they're considered to be anti-bonding. So these ones are below the line, so they're considered to be like, bonding molecular orbitals. So no stability is gained here. This is anti-aromatic. Stability is gained here. This is aromatic. So this is the orbital representation of, why we have aromatic, why we have anti-aromatic. Cool. Here, all 6 electrons are in the bonding molecular orbital and they're paired. Added stability. Aromatic compounds, the electrons are paired and in the bonding molecular orbital, so they're below this line. Anti-aromatic compounds are unpaired and or in non-bonding molecular orbitals, so they're above this line, or they're on the line. Okay, that wraps it up for resonance structures. And you guys will cover one last topic, substitution reactions. So that's a topic that you'll also cover again in 109B. So if you want to cover the substitution topics, just watch the first part of the 109B video, the first 109B video.